Hello everyone. Today we're going to discuss ethers and ether synthesis. Ethers are compounds with functional group such that oxygen is attached to two alkyl groups. In other words, the oxygen connects to two alkyl groups. Example of ethers are CHF, which is the acronym for tetrahydrofuran, and diethyl ether. In terms of the general properties of ethers, these compounds are extremely very stable, and as such, we generally use them as solvents to run reactions. How can we synthesize ethers? If you consider this ether, one of the things you can do is to split the molecule right here, and that would disconnect this compound into two groups, the R group and the OR prime group. So if you split this molecule into two at that junction, for the R group, what you can do is to add a leaving group to it. Generally, you could use halogen, any of the halogens such as chlorine, bromine, or iodine, or you can use OTS. You can convert it to tosylates. Now, for the OR prime, you can make that into a strong nucleophile or a weak nucleophile. To make that into a strong nucleophile, just add a negative charge to the oxygen. Or if you want to make it into a weak nucleophile, then just place a proton in front of the oxygen. So these will be the compounds that will react in order to form the ether. Another thing we can do is that if you don't want to split it right here, you can also decide to split the compound through this bond. If you split it right there, you will have two fragments. You will have the OR fragment and you will have the R prime fragment. You can now make these fragments into meaningful reactants by adding a leaving group to the R prime, which will give you this. And for the OR, you can make that into a strong nucleophile by adding a negative charge to the oxygen, which will be this. Or you can just place a proton or a hydrogen in front of the oxygen, and that will make it into a weak nucleophile, which is what we have here. Now, if you react this compound with this strong nucleophile, that will give you an ether. Or you could react the weak nucleophile. You could react the weak nucleophile, the alcohol, with this alkyl halide, and you should also have your ether. Generally speaking, ethers prefer SN2 over SN1, and that's because whenever we perform SN1 reaction, E1 product always formed as well. And since we don't want to form an E1 product, we just want a substitution product, which is the ether. We generally prefer to run SN2 reaction compared to SN1. Now, the method through which we make an ether via SN2 is called Williams ether synthesis. Essentially, you're going to have SN2 reaction in which a strong nucleophile will react with an alkyl halide, and the alkyl halide generally will be primary or methyl group. And when this reaction occurs, then you will form your ether. The leaving group here can be bromine, chlorine, or iodine, or even the tosylates. Now, as for the strong nucleophile, since this reaction is going through SN2 mechanism, your alkyl group has to be primary, secondary, or methyl. You should never use tertiary, because tertiary will give an E2 mechanism, which will give us the E2 product. So let's look at a couple of examples. So this is the kind of problem you will see on your test 3. So you're asked to fill in the box. Identify the product that would make this, identify or predict the reactant that will make this product, this ether product. So to solve this problem, what you can do generally is to split. There are two ways you can split this molecule into two. One, you can decide to split this molecule here, in which case you will have two fragments. One fragment will have this, and then the other fragment is going to be this other part, which will be this. This generally have two carbons, 1 and 2. Now that we have these two fragments, what you cannot do is to you cannot convert these fragments into meaningful reactants. So the way to do that is we can make this oxygen into a strong, you can give that oxygen a negative charge to make that fragment into a strong nucleophile. And then we can convert the other fragment into an alkyl halide by adding a leaving group to it. Generally, you could use bromine as a leaving group, or you could use chlorine or iodine, or even tosylate or a tosyl group. So if you analyze this, you will realize that the reagent we have here is a strong nucleophile, which could also serve as a strong base. So this is a strong reagent. The alkyl halide is a primary alkyl halide. So when a strong reagent reacts with a primary alkyl halide, you will generally form SN2 mechanism will prevail, and as such, so this is fine. So if you use these reagents, then you earn your full point. Another way we can split this molecule into two is to split it through the other bond. So if you did that, then we would have two fragments. We will have the benzylic fragment, and then we would have this alkoxy group. Again, you want to convert these fragments into meaningful reactants. So for the alkyl group, you can just give that a leaving group, say bromine. And for the alkoxy group, you can make that into a strong nucleophile by adding a negative charge to the oxygen. So here you have a strong nucleophile, which is also a strong base. And your alkyl halide is primary alkyl halide. So after doing this, you must test the mechanism of your reaction in order to see if it can actually make the ether. So if you try to determine the mechanism of the reaction, if it's SN2, then you know that your fragments or your reactants are correct. However, if the mechanism is not SN2, if the reaction is going to do a different mechanism from SN2, then you don't want to use those fragments or those reactants, because those will not form the ether. Right? For example, if the prevailing mechanism is E2, then you're going to form an alkane and not the ether. So here, alkyl halide and strong will also give you SN2 mechanism. Therefore, this will also fly. So either you use these reagents or you use these reagents. Either one will give you the correct answer. In other words, we can now conclude that either of the above conditions will favor SN2 mechanism. The above conditions will favor SN2 mechanism. Therefore, either reagent will work. So let's go over another example or another problem. Again, you've been asked to fill in the box or complete the box. So here we have this ether, and we're asked to predict the reagent or reactants that will combine together to form this ether. So what we're looking for is a reaction that could do SN2 mechanism. So to do this, we will need to split this molecule into two. We can decide to split it here first. If you did that, then we will have two groups. You will have the alkoxy group and you will have the methyl group. So now that we have these two fragments, we can now convert these fragments into meaningful reactants. So we know that for SN2 mechanism, the nucleophile has to be strong. So a strong nucleophile needs to have a negative charge. So give this oxygen a negative charge. And regarding the methyl group, we can convert that into an alkyl halide by attaching a leaving group to the methyl group. So we could give this a Br. Now we have methyl bromide. So your alkyl halide is methyl bromide, and your nucleophile, this is a strong nucleophile, which also doubles as a strong base. So these conditions will give us SN2 mechanism. That means if you choose both of these reagents, you would have chosen the correct answer. What if we decide to split this molecule here? If we split that molecule there, then we would have two fragments. You will have the cyclohexane fragment and you would have the alkoxy fragment, or CH3. So we need to make these fragments into meaningful reactants. To do that, we will need to make this alkyl. We will need to convert that alkane fragment into an alkyl halide by giving this a bromine. And then we can make the methoxy group into a strong nucleophile by adding a negative charge to the oxygen. So the type of alkyl halide we have here is a secondary alkyl halide. And for the nucleophile, we have a strong nucleophile, which is also a strong base. Now, when you have strong reagents and a secondary alkyl halide, the mechanism that prevails is going to be E2. So E2 mechanism will not give you ether. Okay, E2 will give you an alkene as a product. Therefore, this reagent will not work. And that's because those two variables will give you E2 product, which we don't want. Therefore, on your exam, if you select these two compounds, then you will be marked wrong. So whenever you split your product into two fragments, always test to see whether the reagent you convert the fragments to will give you an SN2 mechanism. If it does, then that will be the correct answer. If it doesn't, then that will be an incorrect answer. Let's make some progress. The next thing we'll be discussing will be making of ethers. How can you synthesize ethers via SN2 mechanism? To make an ether via SN2 mechanism, you need a strong nucleophile. So you would have your strong nucleophile. Usually, the strong nucleophile is also a strong base. And of course, you will have your alkyl halide. Your alkyl halide generally should be primary or methyl. So this reaction will go through SN2 mechanism to give you your ether. So essentially what happens is that the strong nucleophile will attack this electrophilic carbon from the opposite side as the leaving group and then kicks out the leaving group. In which case, your product would then be this ether. That's going to be your product. So your alkyl halide cannot be secondary and it cannot be tertiary. Because if it is, then the product is going to be an E2 product. Another method through which we can make an ether is via acidic conditions. So making ethers via or under acidic conditions. Making ethers under acidic conditions. So generally there are two types whenever you want to make an ether under acidic condition. The first method is dehydration of alcohols. Dehydration of alcohols. So when you have two alcohols combining together under acidic conditions, the catalytic acid you will use here could be catalytic sulfuric acid, or you could use catalytic tosyl acid, or paratoluene sulfonic acid, p-toluene sulfonic acid. And the structure is this. So you have toluene. Toluene is when you have a benzene ring with methyl group on it. So this is toluene. The toluene is connected to sulfonic acid. Sulfonic acid is sulfur with these oxygen that are doubly bonded to sulfur. And you have OH here. So this is paratoluene sulfonic acid. Whenever it's paratoluene because the CH3 and the sulfonic acid group are para for each other. When they're in this position from each other, we call it the para position. All right, so whenever you do this type of reaction, then you're going to form an ether. So essentially, water is lost in the process. So dehydration simply means removal of water or loss of water. So when you remove this water, whatever is left will then combine together. So you're left with R and OR. So that will give you your ether, R and OR. So let's write right here, remove water. Now this reaction generally follows SN1 mechanism. Now for this reaction to work, since the mechanism is SN1, that means one of those alcohols must be, at least one alcohol must be secondary or tertiary alcohol. So one of those two alcohols must be secondary or tertiary for this reaction to work. Now the second type, let's call this A, dehydration of alcohol. Then we're going to have B, reaction of alkene with alcohol. So we're reacting alkene with alcohol. So we're going to do this also under acidic conditions. So you're going to use a catalytic acid, such as catalytic sulfuric acid. So in this case, there are two groups, the hydrogen and the OR group. So the hydrogen will add to the less substituted carbon of the alkane, and then the OR group will add to the more substituted carbon of the alkane. This follows Markovnikov addition. So in other words, you're going to break the pi bond of the alkane and add hydrogen to the less substituted carbon, and OH, or OR rather, OR to the more substituted carbon. Since we don't usually show the hydrogen on carbons, can erase this. So this is going to be your product. So notice here that the OR group, or the OR prime group, is attached on the more substituted carbon. More substituted carbon of the alkane. Like I mentioned just now, this reaction is a variant. It's a variant of the reaction involving alkene and water and catalytic sulfuric acid. So we learned this reaction a couple of lectures ago, in which case we will break the pi bond and attach hydrogen to the less substituted carbon and OH to the more substituted carbon. And since we don't generally show the hydrogen on carbon, this is what we have. So you guys should recall this reaction that we learned a few lectures ago. All right, so these are the two types of reactions we could use to make ethers under acidic conditions. So we're going to discuss these individually. So let's start with the first one, the A. The A is also known as acid-catalyzed dehydration of alcohols to form ether. Acid-catalyzed dehydration of alcohols to form ethers. So what this simply means is that we're going to be reacting excess of the alcohol, or two equivalents of the alcohol, with catalytic sulfuric acid, or any catalytic acid at all. So this is going to form ether. A couple of examples will be, if you treat cyclohexane, excess cyclohexane, with catalytic sulfuric acid, product is going to be ether. So the way this works is, so you have alcohol, then you have another equivalent of the alcohol. Remember, I said that this reaction is acid-catalyzed dehydration. Dehydration means we are removing water. So we're going to remove H2O. Now, whatever is left is what will be the product. So we have oxygen. So that oxygen will be connected to this carbon and this carbon. So a product will be, so this carbon will be connected to the oxygen. This oxygen is connected to this carbon, and then you have this product. So let's look at another example. So let's say we're asked to determine the product of this reaction, where when we treat this alcohol under acidic conditions. So determine the product of this reaction. So the way this works is, again, you're going to have two equivalents of this alcohol. So remove water from this reaction. So whatever we have left is going to be the product. So here we have this oxygen, which is connected to this carbon. And that oxygen will also be joined to this carbon. And so our product will be oxygen connected to this group. And that will be the product of the reaction. Easy peasy. So this should be minus H2O. Another example. So we're told that if you treat this excess alcohol with catalytic sulfuric acid, what's going to be the product of the reaction? Now, recall that we did mention that for this reaction to work, one of those alcohols have to be secondary or tertiary alcohol, because the reaction usually goes through the reaction goes through SN1 mechanism. So here we have a primary alcohol. Because this is a primary alcohol, therefore this reaction will not work. So you would have no reaction. Reason being that the alcohol is a primary alcohol. I know that the question you'll be asking will be why. Why is it that this particular alcohol that is primary doesn't give us any reaction, whereas the other secondary and tertiary alcohol gives us a product? Well, the answer to that question lies in the mechanism of the reaction. So let's quickly examine the mechanism of this reaction. So let's say we have two equivalents of this alcohol reacting under catalytic sulfuric acid. So we know that the product will be this ether. So how does it work? What does the mechanism of this reaction look like? So whenever a reaction is taking place under acidic conditions, the first step of that reaction is going to be protonation. That's going to be the very first step of the reaction. And why? Why are we protonating? So when you have two compounds like this, one of them is going to be your nucleophile, and then the other one is going to be the electrophile. So let's say this is a nucleophile, and here is our electrophile. Nucleophile always reacts to the electrophile. However, here we have weak nucleophile. We also have a weak electrophile. So if you have a weak nucleophile and a weak electrophile, the reaction might take forever and nothing's going to happen. So you need to find a way to make one of them reactive. Okay, and that's what we do by protonating one of the compounds. So we protonate the electrophile to make the electrophile to be strongly electrophile, to be very reactive. So that's the reason for protonation. So treat the electrophile, or one of the molecules of the alcohol, treat it with the sulfuric acid, the catalytic sulfuric acid. So we say the first step is protonation. In protonation, the lone pair on the oxygen will go on to grab the acidic proton of the sulfuric acid. The bond between hydrogen and oxygen will break, and the excess electron will form a negative charge on the oxygen. So here, you would have hydronium ion, and you also form the conjugate base of the acid. Now, the leaving group this is an excellent leaving group. Why? Because if the compound leaves, if the leaving group leaves, it's going to form a stable molecule. So positive charge on an oxygen makes that oxygen extremely unstable. That oxygen needs electrons. So it's going to pull electrons from the nearby bond, from nearby sigma bond, and that bond will break away. The bond will break and you will form a carbocation intermediate. Carbocation intermediate. And that is your electrophile. And of course, the leaving group, when it leaves, will form a neutral, stable water molecule. So now that the electrophile has been made to be very reactive, we can now react that electrophile with the weak nucleophile. And of course, you know that we always draw a curved arrows from electron source, such as lone pair. So the lone pair of the nucleophile. So we draw the curved arrow from that lone pair towards the electrophile, the atom that is electron deficient, which is the carbon in this case. So when this happens, the oxygen is going to form a bond with the carbon. That oxygen is attached to isopropyl group, and that oxygen also has one proton. So now, because oxygen has 3 bonds, it will gain a positive charge. We need to get rid of the positive charge. To do that, we will need to use a base to pull off that proton. So the base we're going to use will be this conjugate base that will form in step 1. Again, we always draw curved arrow from electron source. So the electron source is the lone pairs on this oxygen. This oxygen has 3 lone pairs. So we draw the curved arrow from one of the lone pairs on the oxygen towards this electron deficient proton. The bond between hydrogen and oxygen will break, and the excess electron goes on to the oxygen to neutralize the positive charge on that oxygen. And our eventual product will be the ether. And the catalytic acid will be regenerated. And that's going to be, and this will be the mechanism of the reaction. So this is generally an SN1 mechanism, right? Because from here, the leaving group leaves, forms a carbocation. The carbocation then reacts with a weak nucleophile. Okay, so you're going to have a SN1 product. We also know that SN1 and E1 always occur pari passu. They always occur together, right? So that means we could also form an E1 product. So E1 product can also form. But even if it forms, it will eventually it will eventually form an ether. And why this could also undergo E1 mechanism is that from here, the leaving group leaves, forms the carbocation intermediate. This weak nucleophile can also act as a weak base. If it acts as a weak base, it's going to pull off a proton from this beta carbon, and that will give you an E1 mechanism. So we will discuss that E1 mechanism in the next reaction. So the very next reaction will be acid-catalyzed addition of alcohols to alkane. Acid-catalyzed addition of alcohols to alkanes. So if you have an alkane and you treat that alkane with alcohol under acidic conditions, so the hydrogen from the alcohol will add to the less substituted carbon, whereas the alkoxy group of the alcohol will add to the more substituted carbon. So your product will be such that you break the pi bond and add the alkoxy group to the more substituted carbon, and you will form your ether. So let's say we form an alkene, we form an E1 product here. That E1 product can also react with more alcohol and form ether. So let's go over a couple of examples. So if you treat this alkene with, say, methanol under acidic conditions, what's going to be the product of this reaction? The product of this reaction will be such that you will break the pi bond and then attach the methoxy group. So hydrogen goes to the less substituted carbon, and the OCH3 group will go to the more substituted carbon. This is your less substituted carbon, and this is your more substituted carbon, which is where we'll add the OCH3 group though. So we don't usually show hydrogens on carbon, so I would erase the hydrogen. Another example, if you treat this alkane with this alcohol, butan 1-O, this is 1, 2, 3, 4. So butan 1-O. That's the name of the alcohol. So this reaction is taking place under acidic conditions. What's going to be the product of the reaction? Now, this carbon if you look at the alkene group here, carbon 1 is the less substituted carbon, and that's just because it has only one alkyl group coming off of the carbon. And the carbon 2 is the more substituted carbon, and that's because it has two alkyl groups coming off of that carbon. So this reaction generally follows Markovnikov addition, in which case if you break the pi bond, you add hydrogen to the less substituted carbon, carbon 1, and this alkoxy group be attached to the more substituted carbon 2. So the product of this reaction will be such that break the pi bond, add hydrogen to carbon 1, and the alkoxy group will be attached to carbon 2. So the oxygen forms a bond with the carbon 2. That oxygen has 4 other carbons attached to it. So you have 1, 2, 3, 4. And that's going to be the product of the reaction. It's easy and straightforward. Now, what does the mechanism of this reaction look like? That's what we'll be considering shortly. So here we are reacting an alkene with an alcohol, specifically ethanol, and the reaction is taking place under catalytic sulfuric acid. So we break the pi bond, we attach hydrogen to this less substituted carbon, and the ethoxy group is attached to the more substituted carbon. So to draw the mechanism of this reaction, we can start out with the alkane and then treat the alkane with catalytic sulfuric acid. So whenever you're doing mechanism under acidic conditions, the first step is always protonation. So draw the curved arrow from the pi bond, which is your electron source, towards the hydrogen or proton of the acid. The bond between hydrogen and oxygen is going to break, and the excess electron will go on to this oxygen. So you will end up forming. So when you break that pi bond, this is carbon 1, this is carbon 2. So hydrogen will always go to carbon 1, and then the positive charge will be on carbon 2. So we're going to form a carbocation intermediate, a secondary carbocation intermediate. Of course, the conjugate base of the acid will also form. Next, we can now react the alcohol with the carbocation intermediate. So we're going to draw the curved arrow from electron source, which is the lone pair on the oxygen, towards the electron deficient carbon of the carbocation intermediate. So the oxygen will form a bond with the positively charged carbon. And recall that the oxygen has an ethyl group and a hydrogen. So here is the ethyl group and here is the hydrogen. Since oxygen have 3 bonds, it will gain a positive charge. So we need to remove the positive charge on the oxygen. To do that, we're going to have an acid-base reaction. Since this compound has excess proton, we want to get rid of the proton to neutralize the positive charge. So you will need a base to abstract that proton. Okay, and that's what makes this acid-base reaction. So we're going to use the conjugate base of the acid that was formed in the first step. We'll use that conjugate base to remove that proton. To draw the curved arrow from the electron source towards the electron sink, the bond between hydrogen and oxygen is going to break, and the excess electron goes on to neutralize the positive charge on the oxygen. This would then lead to the formation of our product, the ether, and the catalytic sulfuric acid is regenerated. So I'll go on to give us a few tips on how to draw mechanisms for acid-catalyzed reactions. So tips on how to draw mechanism. For acid-catalyzed reactions. Acid-catalyzed reactions. Firstly, each step of the reaction will be reversible. Each step of the reaction will be reversible. Secondly, the nucleophile is usually water or alcohol, and this also serves as the solvent. So the nucleophile is usually water or alcohol. And the nucleophile, the water or alcohol, usually will also serve as the solvent. Also serve as the solvent. Another thing to note is that each bond forming or each bond breaking process will be preceded by protonation. In other words, the first step is usually protonation. So each bond forming or bond breaking step will be preceded by protonation. Fourthly, your intermediate should be positively charged. Let's say most intermediates will be positively charged. Fifth, the only negative charge that you're allowed to form under acidic condition is the conjugate base. And that's because the conjugate base is usually, I remember that we normally use catalysts in trace amount, in very small quantity. So even if it forms a conjugate base, it's usually negligible because the concentration is extremely, extremely low. So the only negative charge you're allowed to form will be the conjugate base. So you cannot form strong nucleophiles. You cannot form strong nucleophiles in acidic conditions. Remember that strong nucleophiles are usually negatively charged. The other species or compound that is negatively charged is base, right? So in other words, and we know that strong nucleophiles can be strong, or strong nucleophiles can also be, most times are also strong bases. So whenever you form negative charges, that means you are forming a strong base. And you can't be forming a strong base when the reaction mechanism is acidic. Okay, this is why you are not allowed to form negative charges under acidic conditions. Lastly, the last thing to note when drawing mechanism under acidic condition is that in the first step, you will use the catalyst in the first step. And then in the last step, you would reform the catalyst. In other words, your first step has to be protonation, and then your last step shall be deprotonation. So the first and last steps, are using and reforming the catalyst. Using and reforming the catalyst. So in the first step, you use the catalyst. In the last step, you reform the catalyst. So the next reaction we'll be discussing will be hydrolysis of ether. Hydrolysis of of ethers. Hydrolysis simply means addition of water. So if you react an ether with water under acidic conditions, you will form alcohol. So this is the reverse of the reaction we've been discussing. Again, alcohol, ether and alcohol are weak. They're weak species, right? They're weak nucleophiles and weak electrophiles. Okay, if you just combine both of them, nothing is going to happen, which is why we usually speed up the reaction using this acid catalyst. So all you have to do is make this into alcohol and also make this into alcohol. So your product will be alcohol and another alcohol. So if this is R prime, then we'll have the R prime here. But for this to work though, your ether, one of those alkyl groups, either the R group or the R prime, must be secondary or tertiary. For example, if you treat this ether with water under acidic condition, what's going to be your product? So notice that at least one of them is a tertiary alkyl halide. This group here, the alkyl group here is tertiary alkyl halide. So this reaction will work. So all you have to do is to add OH to this group and OH to this group. So if you did that to make this into an OH group, you have that tertiary alcohol, and then you would have a methyl alcohol. So that's all you have to do. Another example, let's say we treat this ether with water under acidic conditions. What's going to be the product? Again, add OH group to this and add OH group to this also. So add OH group to this carbon and another OH group to this carbon. So you would have two equivalents of cyclohexanol. Also notice that this is a secondary alkyl halide. This is also secondary alkyl halide. And the condition requires that one of those alkyl groups should be secondary or tertiary alkyl halide. So this reaction will also work. Another example, if you treat this ether with water and catalytic sulfuric acid, what's going to be the product of the reaction? So if you look at this alkyl group on the left hand side, it is not secondary and it's not primary alkyl. It's not secondary or tertiary. This also is not secondary or tertiary. Okay. Therefore, this reaction will not work. So we're going to have no reaction. Because the reaction condition is that one of them has to be, at least one of them has to be secondary or tertiary. And that's because this, in the mechanism of the reaction, it goes through the formation of carbocation intermediate. And we know that primary carbocation or methyl carbocation are not stable. That's why the reaction will not work. If you want to see the mechanism proper, that's what we'll be discussing shortly. So we have this ether, which we treat with water and catalytic sulfuric acid. So we say that this is going to form tertiary alcohol and methanol or methyl alcohol. Why? So the first step of this reaction is that since this reaction is taking place under acidic conditions, the first step is going to be protonation. You must start with protonation. So we treat this ether with the catalytic acid. So to draw your curved arrow, we always draw curved arrow from electron source, in this case, the lone pair on the oxygen, towards hydrogen, the proton of the sulfuric acid. The bond between hydrogen and oxygen will break, the excess electron will go on to the oxygen, and we will end up forming protonated ether. So we'll have this hydronium ion. That oxygen gains a proton, and because oxygen now have three bonds, it will have a positive charge. And you will form the conjugate acid, the conjugate base of the acid. So here will be the conjugate base of the acid. This is an excellent leaving group. Why? Because if it leaves, it will form a neutral molecule. So that's exactly what's going to happen. The oxygen that is electron deficient is going to pull electron from the nearby bond, single bond. Bonds are sources of electrons as well. So when that happens, you will form a carbocation intermediate and you will form the leaving group. So when the leaving group leaves, it forms a neutral molecule, which is why it's an excellent leaving group. Now, the carbocation intermediate is very reactive. This carbocation intermediate that is reactive can now react with a weak nucleophile. So we draw the curved arrow from electron source, which is the lone pair on the oxygen, towards the electron sink, which is the positively charged carbon. So this way, a new bond will be formed between that positively charged carbon and oxygen of the water molecule. That oxygen has two hydrogens. These are the two hydrogens here. So when the oxygen with the two hydrogens now forms a bond with the carbon, that oxygen will now have three bonds. Because it has three bonds, we will give it a positive charge. Now we need to get rid of the positive charge on the oxygen. And why it has a positive charge is because it now has excess protons, which makes it an acid. So if you want to remove the proton from an acid, what do you use? You use a base. So we're going to bring that conjugate base up here and use it to remove the proton on the acid. So to draw your next curved arrow, draw it from the electron source towards the electron sink. So you have your acid-base reaction. Now your final product will be this tertiary alcohol, and of course, the catalytic acid is regenerated. So the alcohols that we formed here are this, which is tertiary alcohol, and this methanol.